Hi, welcome to this video series about motion on a straight line. To describe the motion of an object, there are some terms or physical quantities that you can use. In this video, you will learn how to describe and calculate the position, distance traveled, and displacement of an object. I have also discussed a few sample questions at the end of the video to help you apply what you learn. So let's get started. We shall first discuss how to describe the position of an object on a straight line. Now assume there is a straight road on which there is a house A, a house B, and a restaurant R. The distance between the houses A and B is 200 meters, and the distance between the house B and the restaurant R is 300 meters, as you can see. Suppose you were asked to describe the position of house B in this picture. How would you describe its position, or how would you describe its location to another person? Go ahead and try. Now, if I had to describe the position of this house, the house B, I would say it is 200 meters to the right of house A. Now let's talk about this. 200 meters to the right of house A. Now there are three elements that you need to notice here. The first element is this magnitude 200 meters. The next one is the direction. We are saying that B is 200 meters to the right of something. Right indicates direction. So there's a magnitude and there's a direction as well. The third element that you need to notice is the reference. We are saying that the house B is 200 meters to the right of house A. So house A is the reference. Now, if you don't know where house A is, there's no way you can locate house B using this information. So to describe the position of an object on a straight line, we need a reference. And the position can be indicated by specifying a magnitude and a direction from that reference. You could also have indicated the position of the house B by taking the restaurant as the reference. You could say it is 300 meters, that is the magnitude, to the left, that is the direction, of the restaurant R, which is the reference. Now if you notice, we have naturally used the directions right and left in this case. It is also possible that this is the eastward direction and the opposite is the westward direction. So we can use east and west as the directions as well. We could even use north and south, any two opposite directions. Now if a straight line is vertical, we could name the directions as up and down. A straight line always has two directions. If the straight line is horizontal, you can describe the directions or call them as left and right, east and west, north and south. If the straight line is vertical, you could call them as up and down. Instead of using these many different names in different cases, we usually use only two terms. One direction would be called positive and the opposite direction would be called negative, as you see here. Now there's no rule as to which direction should be called positive. So I'm considering the rightward direction as positive, I'm indicating it with a plus, and the leftward direction as negative, I'm indicating it with a minus. So we are no longer going to use left and right as the directions, we are going to use negative and positive. Anything directed towards the left will be given a negative sign, anything directed towards the right would be given a positive sign. To describe the position of an object, we also need a reference. The reference is called as origin of a reference frame. In this case, let us consider A as the reference. So A would be called the origin of this reference frame. Now that we have fixed a reference frame, we can try and describe the position of the house B in this reference frame. The house B is 200 meters towards right from house A. So if you put it mathematically, you should say it is 200 meters towards the positive direction of the origin. So we can now write the position of the house B, RB, as plus 200 meters. It indicates that it is 200 meters away from the origin towards the positive side. Now go ahead and try to describe the position of the restaurant R in this reference frame. The restaurant R is at a distance of 200 plus 300, that is 500 meters away from the house A, and it is towards the right side. So mathematically, we can describe its position as position of R is plus 500 meters, indicating that it is at a distance of 500 meters from the origin towards the positive side. Now there's no rule that the origin should always be kept at the first object. You can even consider the origin to coincide with the position of house B. Try to describe the position of house A in this new reference frame now. The house A is at a distance of 200 meters to the left of house B. So it is 200 meters from the origin towards the negative side. So we can write the position of house A as RA equals negative 200 meters. What it means is that it is 200 meters away from the origin on the negative side. Now, if you want to indicate the position of the restaurant R, you can indicate it as RR equals plus 300 meters. Now, the positive sign is usually omitted. So in case there's no sign in front of the magnitude, you'll assume it to be positive. The plus 300 indicates that it is at a distance of 300 meters from the origin. Now, why are we using a bar over the symbol of position? This is to indicate that it is a quantity which has direction. It is a vector quantity. In physics, you will come across some quantities which do not need a direction and some quantities which are defined along with a direction. Such quantities which are defined along with a direction are called vector quantities, and position is one such quantity. So we place a bar on the symbol of position just to indicate that it's a vector quantity. Now, whenever motion happens on a straight line, you can consider an axis along that straight line. For example, you can call this as the x-axis. Now, any position on the x-axis will be indicated with an x coordinate. For example, since we have fixed the origin here, we can say that the position of house A is xa equals minus 200 meters. And the position of the restaurant R is xr equals plus 300 meters. So we can indicate position on a straight line by using just one coordinate. For example, that coordinate for A in this case is minus 200, and that coordinate for R in this case is plus 300. So this is how you describe the position of an object on a straight line. You first need a reference frame, which is nothing but a straight line with an origin on it, and then you can specify the position of any object relative to that reference, relative to that origin. We shall now discuss how to describe the distance traveled by an object. By definition, it is the total length of the path traced by an object. For example, let's suppose this delivery boy starts from the house A, goes to the restaurant, picks up the pizza, and then delivers it at house B. Now we want to describe the distance traveled by this person. So let's trace out the path followed by him. The person starts from house A, goes straight to the restaurant R, as you can see, and then comes back from R to B. Right. Now the definition of distance, as you have just seen, is the total length of the path traced by an object. Now you have seen what the delivery boy did. He started from A, went straight to the restaurant R, and then came back to the house B to deliver the pizza. Now use the definition of distance, and on your own, try to calculate the total distance covered by the delivery boy. It's a simple exercise. I think you will be able to do it on your own. Make it quick, and I will explain it to you. Hope your answer is ready. The delivery boy started from A, went straight to R, and then went from R to B. Now the distance covered when the delivery boy goes from A to R is 200 plus 300, that is 500 meters. And the additional distance covered when he goes from the restaurant to B is another 300 meters. So the total distance traveled would be 800 meters. And notice here that we do not place a bar over the symbol for distance, because distance covered by an object does not have a direction assigned to it. We just say it has covered a certain distance. We don't mention a direction. You'll learn about something called displacement, which is the next quantity that we discussed, which comes along with the direction, but it has a meaning of its own. So basically, this is how you calculate distance traveled by an object on a straight line. You need to know exactly how the object is moving on that straight line. And now we shall discuss displacement, which is quite often defined as the shortest distance between 2 points. But this definition is wrong. It is actually the change in position of an object. Displacement is not just the shortest distance between 2 points, it also indicates the direction from the initial position to the final position of the object, as we shall discuss in detail now. Right. Let us understand the idea of displacement using the same example where the delivery boy started from A, went to R, and then came back to B. So the initial position of the delivery boy is A, as indicated with the green marker, and the final position is B, as indicated with the red marker. Now displacement, by definition, depends only on the initial and final positions of an object. It does not matter how the object went from the initial to the final positions. It might have gone straight from A to B, from the initial to the final positions, or it might have gone somewhere else in between and then reached the final position. Let's understand why displacement depends only on initial and final positions. Now the definition of displacement says that it is the change in position. Now change in any quantity is nothing but the final value of that quantity minus the initial value. So we can say that displacement is the final position of an object minus the initial position of the object. RF indicates final position, RI indicates the initial position, which can also be written as delta R. Now let's consider origin to be at the house A. Then the position of house B will be written as plus 200 meters. Now if you want to calculate the displacement of the delivery boy in this case, the final position is plus 200 minus the initial position is 0. So the displacement turns out to be plus 200 meters. Now notice that we have placed a bar on the symbol for displacement, meaning that it is also a vector quantity. Now we have derived the displacement in this case as plus 200 meters. What it means is that the delivery boy has undergone a displacement of 200 meters towards the positive direction. We can indicate that displacement using an arrow like this. We can indicate that displacement using an arrow like this. The direction of the arrow shows the direction of displacement, and its magnitude is 200 meters. This is why we say that displacement depends only on the initial and final positions. It is defined like that. Now, why do some people say that displacement is the shortest distance between 2 points? Now, if you observe, the magnitude of displacement is 200 meters. 200 meters is the shortest distance between house A and house B. If you go straight from A to B, you would have to cover 200 meters. If you take some other route, you'll have to cover a distance of more than 200 meters, but the shortest distance between A and B is 200 meters, which is only the magnitude of displacement. Suppose the person undergoes a displacement like this, 200 meters towards left. That is negative 200 meters. Now the displacement in this case is negative 200 meters minus 200 meters, but the shortest distance between A and B will still be called as 200 meters itself. You would never use a negative sign to indicate the distance between 2 points. You will still say the distance between A and B is 200 meters, but the displacement is negative 200. So it is not correct to say that displacement is the shortest distance between 2 points. Magnitude of displacement is the shortest distance between 2 points, but displacement has something more to it. There is a direction that must be assigned. So remember that displacement is the change in position of an object. It can be calculated as the final position minus the initial position. Now in this example, we have done that for motion on a straight line, but we use the same definition even in case of motion in 2 dimensions or in 3 dimensions, as you will see later. As an example, assume the delivery boy starts from B, goes to house A, and then goes to the restaurant R. So B to A to R. Calculate the total displacement in this journey. Right, let's see how to calculate the total displacement. Now displacement by definition is the change in position. So you need to know what was the final position and the initial position. The initial position from where the delivery boy started is the position of the house B, which is plus 200 meters. And the final position is the position of the restaurant, which is plus 500 meters. Then the change in position, if you calculate R final minus R initial, 500 minus 200 would be plus 300 meters. What it indicates is that the delivery boy has undergone a displacement of 300 meters in the positive direction, and it makes sense. Let us draw an arrow from the initial position to the final position and see if it indicates the same thing or not. The initial position in this case is the house B, and the final position is the restaurant R. And this arrow has a length of 300 meters, and it's pointed towards the positive direction. So the displacement indicated by it is plus 300 meters. So this is how you calculate displacement of an object. It is defined as the change in position of an object, and you can calculate it as final position minus the initial position. In a certain journey, let's say we had to compare the distance covered by an object and the magnitude of its displacement. Assume the object moves from position A to position B on this straight line. So initially it was at A and finally it is at B. We shall consider all possible cases and generalize the relation between distance and magnitude of displacement. We have already discussed that magnitude of displacement is the shortest distance between the 2 points. So the magnitude of displacement would be the length of this arrow drawn straight from A to B. Irrespective of the exact path followed by the object, the magnitude of displacement would always be the length of this arrow drawn from the initial position to the final position. Right. Can distance traveled by the object in this journey be equal to the magnitude of displacement? In other words, can the distance traveled be equal to the length of this arrow? Is there a possibility or not? There is a possibility, and that would happen if the object travels straight from A to B without ever changing direction. So it is possible for the distance covered by an object to be equal to the magnitude of displacement, and that happens only when the object moves without a change in its direction. So we can say that distance equals the magnitude of displacement if the object moves without ever changing its direction of motion. Let's imagine the object changes direction at least once in its journey from A to B. Now, there are infinite possible ways in which you can have a path from A to B, which includes a direction change. For example, the object may go back from A, change its direction, and then start moving forward towards B. Now, in this case, you decide, is the distance less than, equal to, or greater than the magnitude of displacement? Clearly, the distance is greater than the magnitude of displacement because the total length of this blue path is obviously greater than the length of the yellow arrow that we had drawn. Now you can go ahead and consider any of the infinite other paths that are possible from A to B. In every case, you will see that the distance will be greater than the magnitude of displacement. The only possible case in which distance equals the magnitude of displacement is when the object moves without changing direction. If there's a change of direction even once, the distance would become greater than the magnitude of displacement. So we can say that distance will be greater than the magnitude of displacement if the object undergoes any change of direction. Right, so we have our verdict here. It is clear that distance would either be greater than or equal to the magnitude of displacement. And the equality holds when the object moves without changing direction. Now, why this is so important is because most of the equations that we derive in physics involve displacement. But very often you will find questions asking you to calculate the distance. So in such cases, you will need to decide if the object ever changes direction. If it does not change direction, you can use those equations, calculate the displacement, and equate its magnitude to the distance covered. But if it ever changes direction, you will have to split the given time interval into smaller intervals where it does not change direction, then calculate the displacement in each of those smaller intervals, and get the distances in each of those smaller intervals and add them up to get the total distance. You will see one or two such cases discussed in the problems that follow. Let's solve this question, which will help you learn the application of what we have discussed till now. The question says that a boy standing on a bench throws a ball vertically up from a height 2 meters above the ground. The ball reaches a maximum height of 3 meters from the point of projection and then falls to the ground. Considering the upward direction to be positive and the point of projection to be the origin, calculate the position of the ball at maximum height, displacement of the ball by the time it strikes the ground, and the distance traveled by the ball till it strikes the ground. Now there is some information given in the question which will help us visualize the situation and solve the problem. It says that the ball is thrown vertically up from a height 2 meters above the ground. So from the ground, it was at a height 2 meters when it was thrown. The ball reaches a maximum height of 3 meters from the point of projection and then falls to the ground. Now you are also given the reference frame here. Consider the upward direction to be positive. It means that the downward direction or anything directed downwards would be negative. Any vector quantity directed downwards would be negative. And the point of projection is the origin. Right. Now questions in physics become very interesting when you can imagine the situation. Let us do that and then solve this question. Visualize what is happening here. The ball is thrown vertically upward from a certain height. It reaches a maximum height or a highest point in its path and then descends back to the ground. So if you visualize what is happening to the ball, it's something like this. The ball goes straight up and then comes back along the same vertical line. But just for you to be able to visualize, I have used two different vertical lines here. Now it was given to you that the ball is thrown from a height 2 meters above the ground. So this initial position of the ball is already at a height of 2 meters from the ground. And it was also given that it reaches a maximum height of 3 meters from the point of projection. So the distance from the point of projection to the highest point is 3 meters. And we can easily visualize the path followed by the object. You were asked to consider the initial position of the ball as the origin and the upward direction as the positive direction. So it indirectly means that anything directed downward is negative, as I have already told. Now the first part of the question is asking you to determine the position of the ball at its highest point. We indicate the position of an object using a magnitude and a direction by taking the origin as the reference. As you can see here, the highest point of the ball is 3 meters above the origin. So it is at a distance of 3 meters from the origin and it is in the upward direction, which means it is in the positive direction. So how do you indicate its position? The position at its maximum height would be indicated as 3 meters in the positive direction. So you can write it as plus 3 meters. The second part of the question is asking you to calculate the total displacement of the ball by the time it reaches the ground. Now displacement by definition is change in position, which we indicate as delta R. That is R final minus R initial. The final position of the ball is the ground and the initial position of the ball is the point of projection. So we can easily write the initial position of the ball as 0 because the point of projection is the origin. Now the final position of the ball is the ground. Now ground is 2 meters below the point of projection. So we can write that the final position Now 2 meters below the point of projection is negative 2 meters. So the final position, that is the position of the ground, is minus 2 meters. Therefore, the displacement of the ball can be calculated as the final position minus the initial position, which is negative 2 meters. And it makes complete sense because you imagine the ball on the ground finally, it is 2 meters below the point of projection. Now displacement only depends on initial and final positions. It has gone from the point of projection to a certain height and then fallen to the ground. So the total displacement can even be visualized with an arrow like this. It is from here to here. That is a displacement of 2 meters in the vertically downward direction, in the negative direction. That is why we got the displacement as minus 2 meters. The last part of the question is asking you to calculate the total distance traveled by the ball till it strikes the ground. Distance is the total length of the path traced by an object. The ball starts from the point of projection, which you can see in the diagram, and it rises to a certain height, which is 3 meters above the point of projection, and then falls down all the way to the ground. Now, in this case, there is clearly a change of direction happening. So will distance covered be equal to the magnitude of displacement? Can you say the total distance covered by the ball is 2 meters? Definitely not. It is rising by a height of 3 meters and then falling all the way to the ground, during which it descends by 3 meters plus another 2 meters. So there is an ascent of 3 meters and a descent of 5 meters. So the total distance covered by the ball till it strikes the ground would be 3 plus 5, that is 8 meters. I hope you now have a better idea of how to describe the position, distance, and displacement. Let us now look at a question in which the information is given in a slightly different manner. Now, there are many different ways in which questions can be given to you. Three common ways are one that we had seen before, in which a real life situation is described to you. Another way of giving you information is in the form of a graph, which is what we take up in this question. They could also give you information in the form of an equation. Now let's see what this question says. The graph shown here indicates the variation of position of an object on a straight line with time. So this graph indicates how the position of the object changes with time. So it tells you at different times what is the position of the object, as you can see in the graph. So the graph suggests that when t is 0, that is when you start counting time, the object is at x is equal to 0. When t is 8 seconds, the object has gone to 20, x is equal to 20. And at t equal to 10 seconds, the object is at x is equal to 15. If you know some geometry, using this information, you can even calculate its position at times which are not mentioned in this graph. We need to calculate the time, if any, at which the object changes direction. Right. Let us visualize what is happening based on this graph. As I said, at t equal to 0, the object was at x is equal to 0. And as time increases, time is a quantity which always increases. As time increases from 0 to 8, as you can observe in the graph, the position increases from 0 to 20. So basically what is happening here is, in the interval 0 to 8 seconds, the object goes from x is equal to 0 to x is equal to 20. Let us visualize that on a straight line. The object was initially at x is equal to 0. So at t equal to 0, its x coordinate is 0. And at t equal to 8 seconds, it reaches x is equal to 20 meters. And that is the highest point of the graph. So it does not cross the position of x is equal to 20. So let's indicate that on the graph. This is x is equal to 20. It gets here at a time of t equal to 8 seconds. And as indicated by the graph, it continuously travels in the positive direction. Its position goes on increasing till 8 seconds. So it went straight from x is equal to 0 to x is equal to 8 without ever changing its direction. Now after t equal to 8 seconds, as you can see in the graph, the position starts to decrease. The x value starts to decrease. Time continues increasing, but the x value starts decreasing. That means the object is coming back. By 10 seconds, it has come to x is equal to 15. Now x is equal to 15 would roughly be somewhere here. So starting from t equal to 8 seconds, it reaches x is equal to 15 when the time becomes t equal to 10 seconds. And it continues going back as indicated by the graph. So what we have done here is we have visualized the motion of the object based on the graph provided to us. Now let us try to answer the questions that are given here. The time, if any, at which the object changes direction. As indicated by this graph and also as visualized by us, the object is definitely changing direction at t equal to 8 seconds. So the answer to the first part would be t equal to 8 seconds. The next part of the question is asking you to calculate the displacement of the object in 10 seconds. Now displacement, as we know, is the change in position, which is final position minus initial position. So you need to take the position at 10 seconds, which is x is equal to 15. That would be the final position. And from it, you subtract the position at t equal to 0 seconds, which is the initial position, which was the origin. So r initial. Now, if you simply calculate r final minus r initial, you would get 15 minus 0, that is 15 meters, plus 15 meters. And why is it plus 15? Now, displacement can be indicated by an arrow drawn from the initial position to the final position. If you draw such an arrow, it clearly is directed towards the positive side. That is why we got a positive displacement of 15 meters. Now the final part of the question, the distance covered by it in 10 seconds. Distance is nothing but the total length of the path traced by an object. Now as indicated by this graph, the object goes from x is equal to 0 to x is equal to 20 and then comes back to x equal to 15. So it covers a distance of 20 meters when going forward and an additional 5 meters when going back. So the total distance covered by it in 10 seconds is 25 meters. And as I said, you could also be given information in the form of an equation. In such cases, you need to apply your knowledge of mathematics and visualize what is happening based on the equation. You may draw a graph of that equation, or just by looking at the equation, you may directly interpret information from it. But we are not going to take up such cases, at least for now. I hope the ideas of position, distance, and displacement on a straight line are now clear to you. If you have any questions, you can post them in the comment section. And if you found this video useful, like it, share it, and subscribe to my channel. See you in the next video.